And so I'm the analyst. So if the building is the 4th floor, so I assume height is 12 meters. And let's first take a look at motion formula. So if no delta x, we can say velocity equals VO plus AT. And if no V, first we can say delta x equals VOT plus 1 over 2 AT squares. And let's take a look at the first one physics phenomenon for G equals 9.8 meters over time square. So by my conclusion, and I get the final V equals 15.3 meter over seconds, and equals 55.1 kilometer over hours. So in this velocity is like getting hit by a scooter going for speed. So if that hit you, you were definitely getting fractures and internal injuries. Yes. And another is and when he jumped up, and I'm assuming teacher M1 is 80 kilogram and student M2 equal 50 kilogram. And I'm assuming the teacher jumps and catch the student whose hand time lasts 3 seconds because he dropped the car and caused 3 seconds. I'm assuming. And I see the inelastic collision is this P equal constant, and P is the conservation of momentum. And V1 M1 V1 plus M2 V2 equals M1 plus M2 and multiply VF. VF is a final all in the systems, and VF equals this. Yeah. And before collision, and it's both like M1 and M2, and we'll make a collision. And after collision, and M1 and M2 is a plus together and make a V final. So by my conclusion, by law of conservation of momentum, and I use this formula, and I get the VF mean 60.04 meter over second. Yeah. So, and another analysis is the kinetic energy and impact force. So, it's still the same assume, and I use this KE equal 1 over 2 mv square, and use the W equal F multiply D, and use the energy concept. So total mass, because I assume M1 equals 80 kilogram and M2 50 kilogram. So it's for 40. Oh, just wrong. So total mass is 120 kilogram, and the car is the defect about 0.5 meters. So EK equal 1 over 2 mv square is use this formula is about 2,188.960. So use this form, we can see the all newtons is 4,377.92. So this contrast. So in real and animate, in real, the human body cannot withstand such an impact, and the car body can be collapsed. Animate, Onizuka and the students were unharmed, but the car was damaged. The car was dented but still existed. So unreal is it just damaged the car, but in real maybe can be burned Yes, and in conclusion, this thing is great. Teacher Onizuka clearly validates several physics principles. The motion involves free fall in elastic collision and a huge impact force. So based on my conclusion, the total kinetic energy is about at least joules, and impact force on the roof is about at least newtons. So in real life, such a force would cause serious injury, but in the anime, both are correct F1. Yeah, this is the end.
Okay, good. But what do you mean by burn? Why is it burning?
I'm assuming that if somebody dropped the car, and because the oil in the car, so when it hit very high powers, damage may be born. I think it should be here.
I'm not so sure about that. So please explain that in your report. I don't agree with that.
Oh.
Yeah. Then also please in the report, please come up with a way to save them. If you put a mattress on the car, can they be saved? Okay. Please discuss that in your report. Okay, other than that, it was very good. Thank you, Randy.
Oh, thank you. Thank you.
Okay, it was good.
Um,
Okay, who's next?
Okay. Okay. Hey. Sorry. Gimana sih? Kok ngalah terus? Hah? Oke. Cara zoom gimana?
Harusnya dia di sini lagi. Dia lagi loading sini.
Ada. Oh. Hah? Masih zoom.
Can you just change the volume?
Okay. Okay, good morning, Professor. So, this is my scene, and
Please explain it for me. You want
okay,
to have 3 minutes.
okay. So Murai here tries bungee jumping from a bridge called Yokohama Bridge in Tokyo, and so. But instead of using a real bungee rope, he uses a nylon plastic rope. Okay, so this is the location of the bridge, which is a real bridge in Tokyo, the Yokohama Bridge.
What's the problem?
So a character named Murai jumped from the bridge with goes bungee jumping with a nylon rope, which is not safe from for bungee jumping. I'll explain here. Okay, right. So the rope. So it is clearly stated in the anime that they go bungee jumping with a nylon plastic rope, which has the property that can stretch only up to 30% before reaching a breaking point, and it elongates about maximum like 30%, and it acts more like a straight line instead of a dynamic line. And so so what's different with the bungee jump cord? And bungee jump cord usually can extend about 200 to like 500% of its normal length, and the material is also rubber. So this is the scene analysis. So first we calculate the speed, which we have 22.1 meter per second, and so this visual image where this a real height of the Yokohama Bridge, and there I already state the wrong formula. So in here, at first I tried using the Hooke's law, sorry, but why cannot we use the Hooke's law? Because the Hooke's law acts as a spring, and the nylon rope does not have that property. The nylon rope is basically almost a static line instead of a dynamic like a bungee jump, and so we cannot use the deceleration, because if we use this formula, it will result in like very small g-force like 3.3 g, with it which is safely assumed is still realistic in real scenario. So what can we use? So we use what's called impulse momentum theorem with shock loading dynamic. So it is basically the same principle when heavy stuff is dropped off a ledge and is tied with a plastic nylon rope. And so why can we use this? It's because the nylon stretches very fast, around 0.05 until 0.08. It's very fast that we cannot use the spring theorem. And so in here we can see that the peak force that we get is around 22,000, and when we put it into with Murray's estimated mass, which is 60 kilogram here, we get a g-force of 38 g, which is very high. And just for perspective, a jet fighter max g-force is around 10, so this is more than it. And also a second one is that we can first see the estimated rope diameter for a nylon, which is about 7.5 times 10 to the power of minus 5, and we can stress it at this force, which we can actually get 289 million Pascal, and that is, and according to data, like the failure point for a nylon is only about 30 to 50 million Pascal, and with 16 to 30 elongation. And also this one, there's the scene also shows like this, which is actually just impossible. But if somehow this happened, and so this is the formula, and I use the energy impact and energy loss here, and to calculate the energy rebound, which if we input everything and find the height rebound, it's about 10 meters, and that is the maximum height. Okay, and so this is the conclusion why that is not possible. And so according to data, the Yokohama Bridge have a triangle support under it, which height is about 13.5 meter. And in the scene, at least Murray rebounded back at least the same height as that support, the triangle support. And so if we just minus the 30 and the 13.5, we get 16.5, which is more than the maximum rebound height. Okay, this is the correction. Okay, so there's two correction. It's either the Murray gave up first, which his leg will at least splinter or like, and his spinal will fraction. And the second correction is either the rope give up first, and so Murray dives to the ocean.
Okay.
Okay.
Excellent. Very good. Very good. So I have a question.
Yeah.
So if this is higher and the rope is longer,
Yeah.
so you said rope is only 30% can be extended, right?
Yeah.
But if the rope is longer, it can extend more, right?
No, because the show explicitly says we use a nylon rope.
No.
That's it.
What
Yeah.
I'm saying.
Yeah.
So okay, 1 meter, 30%, 30 centimeter, right? If it's 2 meters, 60 centimeters.
Yeah.
So if you use a very, very long rope,
Okay.
then the impact time will be longer because rope can extend more.
Yeah.
So the
That makes
impact
sense.
will be less.
Not really. Even if we count and even if we extend to the maximum, like before sea level, let's say the rope is around 45 and we, sorry. Okay.
So so here you have T, right?
Yes, we have T.
T can be longer, right? If the rope is very, very long. So can you consider this in a report?
Okay.
Okay.
Yeah.
But other than
Okay.
that, it was excellent.
Oh, okay.
Yeah, I like that.
Yeah.
Nicholas.
Yeah, Nicholas.
Yeah, you should have calculated that way. G. This one. Okay, anyway. Next person, please. What's your name?
Oh, my name is Felix.
Felix.
So there are two problems here. The first one is he can run down the wall, and the second one, he falls down headfirst from such a height without getting injured.
He's always jumping somewhere. So he was jumping onto the car and jumping onto the pole or jumping into the back of the car.
Okay.
Okay.
So first, let's discuss the first problem. The problem: is it possible to run down a vertical wall? So to answer the question, we need these parameters. And from the internet, I found out that his mass is 55 kilograms, and the normal force will be 0 because he's just running down the wall without pushing into the wall. And so first, we need to find the gravitational force using the formula F equals to mass times gravitational acceleration, and the result will be 540 Newton. And friction, we can use the formula F equals to coefficient of friction times normal force, and the result will be 0 Newton. And to prevent sliding down, the friction must at least be equal to the gravitational force, and this is clearly impossible. So in conclusion, running down a vertical wall without any support is impossible because the friction is 0 and can't counteract gravity. And next problem, is it possible to fall headfirst from such a height without getting injured? And from these two images, we can tell that this building has 6 floors and each floor is 3 meters tall. And so the total is 18 meters. And from these two images, we can know that the cushion thickness is 1.25 meters. And so we have these parameters, and his initial velocity will be 0 meter per second, because based on the conclusion from the previous question, we know that it's impossible to run down a vertical wall. So when he tries to run down, he will slip and fall. So his initial velocity will be 0 meter per second. And so to find the final falling speed and deceleration, we can use the formula of kinematics. For final falling speed, we can use the formula V equals to root of 2 times gravitational acceleration times height. And the result will be about 90 meters per second. And for the acceleration, we can use the formula v squared equals to 2 times acceleration times cushion thickness. And the result will be about 141 meters per second square. And finally, for the impact force, we can use the formula F equals to mass times acceleration. And the result will be about 7.8 kilonewton. And this far exceeds the safe limits for the neck, which is about 3 to 6 kilonewton. And so his neck will be injured because almost all the impact force will be transferred down the cervical spine. And this is what will happen in real life. Yeah, he will just fall down.
Okay, very good. Then for the second part, can you calculate how much boxes they need to survive? You only need a little bit more, right?
Oh, yeah.
Then the first part, why friction zero?
Because by using this formula, coefficient of friction times normal force, but the normal force is 0, so the friction is also 0.
Why normal force is 0?
Because he's just running down, he don't push into the wall, so there's no normal force into the wall.
Is that true? When you're falling down, can you grab the wall and then like this?
But he's running down, so he don't hold the wall.
Maybe true. Okay, maybe true.
Okay, thank you.
So base, can you also calculate a G like U plus B?
Oh, okay.
You had A, but then it's easier than in your example.
Oh, okay.
Okay, very good. Who's next? What's next? Do you have a name?
My name is Wilson.
Wilson.
Yes. And in this scene, there's actually like a lot of action going on, but we're only going to pick one of the problems.
Okay.
And the problem that we're gonna choose is the moment where Onizuka grabs an actual organ and just throws it out in high speed outside the window.
He's gonna fall again.
And then he's gonna jump out. But we're not gonna think about the jumping out part. We're gonna think about the organ.
Okay.
So, first things, I would like the problem is like how is he able to throw something that heavy outside and it's not even horizontal. There's still like an angle upwards and it's in a quite fast speed. So the analysis is like from the video, I can assume that the distance from here to here, we can assume like it's around 5 meters. And judging from the time it took in the anime, it takes from here to here, the organ, it takes 0.3 seconds to reach that part. And judging from the medium-sized pump organs, which is like these kinds of models, it usually weighs around 80 to 120 kilograms. So first we wanted to know the amount of force it takes for him to actually do the thing, to actually throw it this far. So at first, like to know the force, we need to first find the horizontal velocity, so we can actually find out the velocity from here to here. So at first we use this formula, which divides distance with time, which results in the velocity here. And then since we can assume that the angle from the throwing angle is around 45 degrees, and 45 degrees also makes it easier to calculate since the horizontal compound and the vertical one is this exact same. So we can use that to use this formula, and we can find out the actual velocity from here to here, which is 23.58 meter per second. And that is the initial speed that that the organ flew from here to here. That actually starts from him the organ leaving his hand. Okay, so now to find the force, we can use the kinematics formula added with the Newton's law. So with the kinematics formula, we can derive the acceleration of the object when it's leaving from our hand. And like, so the formula is like the v is the velocity of the object, and the s is the amount of time, the distance from the acceleration distance. So we can assume that the acceleration distance is 0.5, and that is from our hand. From here, for example, we throw it like this, and we assume here to here is 0.5 meters. Using that equation, we can combine it to get this singular equation, and it results for the force to be 44,480 newtons. So now let's compare it to one of the actual world records held in real life. And since we actually haven't seen someone throw an actual organ, we can like compare it with something smaller object. For example, like in shot put. In shot put, the world record is held by Ryan Krauser, which he reached the distance 23.56 meters with a metal ball that is around 7.26 kilograms. So we used the projectile motion formula to assume the speed on that formula, the velocity on that formula, on that angle. And we assume the angle is 40 degrees because in actual elite shot put competition, people usually throw it at that angle for the best results. And like, so we get this formula for R is the distance, which is 23.56 meters, and G is the gravity. And then we actually we derived this to find the actual velocity, which is 15.35 meter per second, and we can use the similar formula like we did last time, which is the kinematics formula, and also the Newton's law to also get the force that he used to throw it. And in here, I use the acceleration distance as 2 because in shot put we don't only use our hands but we also use our legs, so we move more. Yeah, and as a result, he used the amount of force exerted is around 427 Newton. And now if you think about it, compared to the organ throwing, this is 100 times more than what this guy did. And I think that throwing an actual organ is quite impossible. So in conclusion, it is actually not real for you to be able to throw something that heavy, that fast, with that much power.
That's fine. But I think it's a little bit unfair. You use 0.5 seconds to throw organ, right?
Yeah.
How much time did you? Here you use. I'm sorry. Here you use a 2 meter, right? And then for organ, what did you use?
0.5.
So there's already 4 times difference there, right?
Oh.
So I felt a little bit unfair, but okay, still conclusion. Okay, good, very good, listen. Yeah, good. Okay, good.
teacher.
Then this year.
Yeah.
Okay. He jumps again.
Yeah. Okay, so in this scene, Onizuka is seen jumping from the swimming pool rooftop, and he jumps like extremely high into the sky. And I think that it's very impossible for someone to do that in real life. And despite falling into the pool at the extreme speed, he is shown floating for like some 3 seconds before finally sinking into the water. Okay, so I'm gonna do some assumptions. First, I calculated the time from the roof to the peak and the peak to the pool. I calculated from the video using a stopwatch. Like, he took 1.72 seconds for jumping from the roof to the sky, and from the sky reaching to the pool is 2.85 seconds. Then the mass is 55 kilogram, height is 1.75 meter, and there's a push-off time, which is the time from the squatting position till he jumps is 0.19 seconds, and there's a body density and water density, which I will use later. So first, I'll calculate the initial velocity that he used when he jumped. It's calculated using the kinematic equations. I calculated it and got a value of 16.856 meter per second with the time of 1.72 seconds to reach the peak. And this means that the character must launch upward at 16.856 meter per second, and this is far higher than any human can achieve. And I also found a world record of the highest jump a person could achieve is 2.45 meter, and the speed calculated is 6.93 meter per second. And Onizuka's speed is like 2.4 times faster than this human's record jumping speed, and it's very impossible for a human to do so. And I'm going to prove it also using the energy and power required to do that jump. Using the kinetic energy formula half mv squared, I got the number of 7,813.43 joules. And the height that he reached is like 14.5 meters. It's very impossible for someone to jump that high into the sky. And the power that required to do the jump in the time push only 0.19 seconds is 41,123.32 watt. And so like this is very impossible. Like a human cannot generate 7.8 kilojoule in a 0.19 second push, and of course a human cannot reach 14.5 meter height, and they cannot output 41 kilowatt power. And this very violates the basic energy limits of a human body. And next, I'm also going to analyze like what happened the moment he enters the pool. First, the velocity when he enters the pool. Also using the formula from the kinematics equations, I got the result of 27.93 meter per second. And next, I'm also going to calculate the force acting on him the moment he enters the water. And to do that, I'm first going to calculate the human volume using the formula of mass over density, 55 over 985. The density is the average human density, and got a volume of 0.055 meter cubic, and the cross-sectional area, which is the length times width. The length is his height, 1.75, and the width is 0.4, which is the average human's width, and got a cross-sectional area of 0.7 meters square. And I got the weight of 539 Newton, and the buoyancy force using the formula of density times the volume times the gravity, which results in also the same as the weight, 539 Newton. And the drag force of using the formula of half times the density times v squared times the drag coefficient and the cross-sectional area. In this case, the drag coefficient is 1 because he falls in a horizontal way, like proning, lying flat, and got a force of 273 kilonewton. And this is a very high number. The drag force is like 500 times his weight, and of course, a human actually cannot survive this, and it's like very dangerous, and he could have
caused like very severe injuries, where in his case, nothing happened. And then there's the floating, which is of course impossible because human cannot survive actually. And so the conclusion, by using the kinematics equation, it's proof that it's impossible for Onizuka to actually jump that high, and he wouldn't survive the moment he entered the water due to the large amount of the drag force.
Okay, very good, very good. So in here he just landed like sideways, right?
Yeah, he landed like horizontal.
If he goes straight, can he survive?
There's a possibility.
Yeah, in a report, can you?
Okay.
Okay. And also, there's another student discussed the same topic, I think last week. So can you read that and then compare the analysis?
Okay.
Okay. But very good, very good. Thank you. And who is next? Jessica.
Okay, so my name is Jessica, and this is my scene I took from episode 3. Yeah, jumping again. But but I focus about but the problem I focus on is didn't really take that long to fall from that height, because if you watch the video, there are 3 POV. The first one is like the third POV, and the second one is Onizuka POV, and the third one is like the principal's POV. But if it's like this one to this one duration, and then we repeat it again to see Onizuka's POV, I think it's too long. And the second one is, can they rotate 180 degrees from head facing ground position into sitting position after they fall? Actually, if the height is too long, I think it's possible, but I think it's only for story building. So from this scene we can see that 1, 2, 3, 4. There are 4 floors until the ground, and the second one is this one is the car, similar. So we can took the height. So the fall descent is from the top of the building to the top of the car, approximately 14.54 meters. Okay. So our assumption here is like the fall distance is 14.54 meters, and Onizuka weight is 55 kilograms. And if we see here, this one is 55 kilograms. In comparison, we can assume the Yoshikawa, because I cannot find Yoshikawa's weight on the internet. So we can assume it's 47 kilograms. So their total weight is 102 kilograms. And we use the gravity acceleration of 9.8. This one is useful formulas for our calculation. The first one is fall time. Is it really took that long? So first one, if we ignoring the air drag, we have the time is only 1.72. After this, we will compare to the video. If we consider the air drag, actually it's not really important, because it's only a difference of 0.02. It won't affect that much. So this one is the first POV is 1.3 seconds, and the second POV is only one POV, but already exceed our previous calculation. So I think our hypothesis is true. And the second hypothesis, the first, they already jump. This one is they have shadow, so they still jump facing ground after 4 meters, after one building, after one floor, and then so the rotation needed is 180 degrees. It's like P radian, and then the fall time is 1.7 74 is the previous one with the air drag. We can assume without air drag. The mass is 102, and the width approximately is 0.5 meters. So I calculate from the height remaining to them to rotate from the previous, they already facing ground for 4 meters. So I reduce 4 meters, so they only have remaining 10 meters, and the time already remains is 0.9 seconds. So the remaining fall time to do the rotation is like 0.881, approximately 0.82 seconds. So the required angular speed is equal to 3.83 radian per second. So we have to rotate in that speed. So the moment of inertia will be 28.16 kilogram meter square. So the required angular momentum to do the rotation is 107.8 kilogram meter square per second. Assume the time they can is like 0.2 seconds. It's possible because we only have 0.8 seconds remaining, and they're in the mid-air, so they cannot have another time. So actually, it's impossible for human. So in our in my conclusion is like in the video is like 2.4 seconds, but our calculation is 1.772. And the second hypothesis is also true because the possible rotation only 33 degrees. Thank you. This one is speed up.
Why did 0.2 seconds to rotate? The second point, you said 0.2 seconds.
Because they have to take the moment to do the force to rotate from this one to like this one, but they only have 0.8 seconds before they go to the ground. And actually, in the mid-air, you cannot take that much time, and also they're holding each other, so it's really difficult to move together. I took 0.2 because we choose very small moment because we cannot take the all 0.8. But if we took 0.4, it's also impossible actually.
Okay. How about the first point? Sorry, can you show me the first point? What was the conclusion?
A fall from this one is like too long because it took 2.4 seconds. But after we calculate, it's only 1.72. It's only one scene, so if we combine with the other POV, it will exceed it a very long time. This one is useful for the second problem.
Okay. So you watched this scene,
Mm-hmm.
and then you thought, oh, falling is too slow. It should be 1.7 seconds instead of 2.4 seconds, right?
Yes.
And then second point is, oh, they are rotating too much.
Yeah. Actually, I want to solve second problem, but
then
I have to find this.
Before thinking about this point, have you thought about they are going to survive or die?
I'm not considering that.
Can you consider that in a report?
Oh, okay.
Yeah, it's still good.
Oh, okay,
So
okay.
maybe can you consider third point if they can survive or die?
Oh, okay.
Okay, good.
Okay, thank you.
Very good. Okay, thanks, Jessica.
Thank you.
Okay. Jerry,
Yeah, there is.
okay. You have to read all.
Okay. Okay, I'm talking about episode 19, and my name is Jerry. Here's my studio ID, and this is the program I provide. And there's two unrealistic things in this episode, and the first is Okay. The riders appeared higher than the bridge level, and which is impossible without an upper initial velocity because the bridge level is horizontal, and it cannot be goes up because there's no upward initial velocity. Yeah, and the second unreal is the Onizuka and his student separate from the motorcycle, but yet later they show embrace in mid-air. So there's the program is, oh. The bad network.
Okay, can you explain in your words?
Okay. And let's start. So it's not only free fall. It's just it has the initial velocity in horizontal. So it's just like the projectile motion. And there's the explanation of projectile motion. The motion of the object thrown into the air and moving under the gravity along the curved path. And there's two types of this projectile. One is horizontal projectile motion, and the other is oblique projectile motion. And the most different is the launch direction. One is horizontally only, and the other is with an angle upward. And it calls horizontally will be the top of the parabola of the curve, because it's only only gravity force to cause him fall down, but it has the initial velocity. But the angle will goes upward compared with horizontal. And here's the list. I list the difference. And the second is momentum conservation, because the second one is the second unreal scheme is they separate first, but the Onizuka embrace his student in mid-air. So there is the momentum conservation I'm provide here. And here's my derivation of formulas. Because the video is post-produced and there's many I need to assume, so I try to derivation of the projectile, and I provide two derivations. One is air resistant, and the other is without the air resistance. I talk first. I talk air without air resistance first, and because it just it has the initial velocity in horizontal, so is the first vertical velocity is 0. So the vertical position is h minus 1 second gt squared, and the time reached the ground is root 2 h over g. So the max horizontal distance is the time which they reach the ground times the initial velocity is I provide here, and I try to consider the air resistance, and before, yeah.
No, I understand. We
Oh yeah. Okay. So there's another derivation of formulas, and we need to the Onizuka need to exert a force on the motorcycle to push him closer to the woman, because there's on the horizontal momentum conservation. So so he needs to exert the force on the motorcycle. Here's my conclusion. If he need to reach a net, here's the diagram I provide here. Here. If they need to reach the net, they need a high velocity horizontal velocity to reach the net, and if they need to reach each other, the Onizuka need to exert a force on the motorcycle to embrace his student, and in totally reach the net and get safe. So it's my conclusion here. And with the error resistance here.
What's the velocity he needs?
Because there's many varieties here, so I didn't assume the varieties where the distance or how long here. So I didn't assume I didn't assume here.
Please do in a
Okay. I will do in.
You need to put the real numbers. This is
Yeah. So because I'm trying to. Yeah. Okay.
Next quiz. You have only 5 minutes. You guys did a good presentation, but you need to prepare this before the class starts.
Okay.
Does that make sense? Okay, someone else is there. Anyone else want to join?
Wait, the presenter cannot join?
No. Are you a presenter?
No.
Then join.
Okay.
Let's start. I saw explosion slide. Someone was saying it's going to explode. The first one is also okay.
But the question is why is it physically safer? Not the not
You're Yanzi, right?
Yeah.
You're the first grade. You get the bonus point. Okay. Yeah, good presentation. You guys. Okay, so now I have 10 minutes for my lecture, which I want to show this. Can you just Google me? Google me. Yeah. Okay. Do you see my screen? Yeah. Okay. So I'm going to talk about this today. Okay. So the train paradox. Okay. So now. Okay. So do you guys? So the topic is Lorentz contraction. Okay. If an object is okay, I need to do this. Okay. All right. I go count. I count. Have you heard of this train paradox? General relativity? No? Okay. Have you heard of this Lorentz contraction? So if an object in general relativity, if an object in special relativity, if an object is moving faster, it gets shorter, okay, by this amount. Okay, if c is very large, right? Speed of light is very large, right? So if velocity is small, it's almost the same. But if you're very fast, close to the speed of the light, then this length gets shorter. Okay, have you heard of that? Okay, it follows this anyway. Now, we consider interesting question. So here comes a train, okay? Here comes a train. Oh wait. Let me mute. Can I mute this? How do I mute this? Here, right? Okay. Okay. When the train comes in, so first, this is a tunnel, okay? This is train, okay? Train is faster, longer than a tunnel. So usually, it's not going to fit in a tunnel, right? But then, if the train is moving very, very fast, near the speed of the light, train gets shorter because of the Lorentz contraction that we just learned, right? So it looks like it's going to fit in a tunnel, okay? But if you are standing here on the train, if you are riding on a train, your train is not moving very fast because the train is stopping, right? Because you are on the train, right? So for this person on the train is not going to get any shorter. Train is the same length. Then it's not going to fit the tunnel, right? Okay. Now here's a question. The moment tunnel, but from people outside, train is very fast, so it's going to shrink and fit in a tunnel. The moment it fits in a tunnel, we close the door. Here, tunnel door. What happens? Is it going to close or it's going to hit the train? So this is a paradox because for people outside, it gets shorter, so it's okay. But if you're on a train is still long, so it cannot fit. Which is correct? So this is train's paradox, okay? Now let me explain, okay? Okay, this is the topic. Lorentz contraction is the topic today. Just ignore this very good-looking guy, okay? Okay, here's what I was talking about here. So okay. So say if it's very fast, it's shrink, right? So it can fit, right? But if you're on the train, why it doesn't? Then it's kind of slow. Why it's not coming? Please. I don't have time. Okay. Here. Now the answer comes. Is this correct? It's not changing. The answer comes. The time, the same time, is not the same for people looking outside and then looking inside. Okay? Wilson, what do you think? Is it going to fit or not? What do you mean? Why no? Can you explain?
The size is smaller than the tunnel, then it's gonna fit.
Okay. So sorry. Do you have a question? So let's look at this situation. Why the screen is not showing? Let me share it again.
I think it's about general relativity.
Okay. So now we think about time. So, what's going on? Say, here's a thunder. Do you see my screen?
The internet in this laptop is kind of slow.
Is it showing?
Is it here?
Can you join again?
Can I'll try to join from my phone and see.
Okay. Then I need to. Can you all join and then look at my slide? Do you have a dongle that I can borrow quickly? Dongle. Oh. can someone join here?
Oh yeah, it's showing. It's showing.
Okay. Okay, so here are two thunders, right? And then thunder comes to this person, and then say A and B at the same distance. This person thinks, okay, thunder happened the same time, right? But if you are here, then the distance from thunder is different, right? This distance from thunder is different, right? So you might think, okay, this happened first, and then this happened later. So it's not the same time for this person. So this is the key to understand this program. Is the screen changing? Oh yeah, it's changing. Good. Okay. Now we look at this right? And if you're looking in outside, it's fine. It just closes, right? But then do you understand that? So for this person, if you're on the train, this door closes first, and then this door closes later, because it takes time for the light to come here, right? Because this guy is moving forward very fast. So if this closes fast, you see the light from here first, right? This light travels a little bit distance. You see it, right? But then this light, when it closes, and then that light comes later because it needs to travel distance, right? So if you are on the train, it looks like for you that this closes first, and then this closes later. So that's perfectly fine. So you close this, and open this, and then after this one goes outside of a tunnel, this one closes. So these two are the same phenomena. It's just depending on where you're watching this, the same time, the concept of same time is different. But still, it's the same physical phenomena, and it's true for both of these. Does it make sense? Or do I need to finish?
So it actually can the box contain the train?
Okay. And then I have a last question.
Because at the speed of the light, it seems like it just close and then open, and then the train pass through.
Okay, sorry. I think I need to finish. Okay. It's time to finish. Any question? You have a question?
Yeah, so the answer is, can the train get contained in the box?
Eh?
Like, can they lock in the train?
Sorry, I don't understand the question. Maybe we can discuss later. Okay. If you don't have a question, maybe it's time to finish class. So thank you very much for presentation. We stop here. If you have a question, please stay here. I can answer. But then we need to first finish the class because it's a time. Okay, see you on Friday. Okay.